Welcome back to Physics 141 online. I'd like to now show the final kind of application of Newton's second law to simple problems involving motion that we'll encounter in this part of the course. And that is now to turn our attention to problems where the object that we're trying to study is involved in circular motion, or at least a portion of a circular path with radius r, moving with speed v. And just to refresh your memory of the result that we obtained earlier in the semester, we showed with a simple vector diagram and some geometry that a particle undergoing this type of motion experiences a centripetal acceleration, sometimes also called a radial acceleration, which is always pointing toward the center of the circular path. And even if that object moves with a constant speed, v, it's still experiencing acceleration because although the magnitude of the acceleration stays the same, the direction is always changing. And so the acceleration is not constant. We can use this equation to solve lots of interesting kinds of problems involving objects that move in circular paths or arcs. And here, let me just set up this example problem and then show you how to solve it. A car of mass m drives over a hill of height h whose shape near the top approximates a circular arc. And the question that we're going to try to answer is this: how fast can the car be moving and stay in contact with the road at the very top of the hill? So what is the maximum speed that it can have when it reaches the top of the hill and still be on the road surface? You can probably imagine intuitively that if a car like this is going too fast, when it reaches the top of the hill, the wheels may actually fly off the pavement and it may become airborne. So we would like to avoid that and be able to post a safety sign, or at least know for ourselves how fast we can drive and still be safely in contact with the road. And now I'll set this problem up and solve it. Okay, let's look at this problem, and I will redraw the sketch that you saw just a minute ago on my slide. It's a little bit hard to redraw it carefully, but it doesn't have to be perfect. It just has to be understandable. So here is the approximate path that this object is taking, and what we're going to do is assume that this hill can at least approximately be regarded as part of a circle. So that here is the circle, and it's said that the hill has a height h, right? So the way that the sketch was drawn, it was clear that that height is the same as the radius of this circular path. So at the very top of the hill, this car is moving, and right at the very top, of course, its speed, v, would be the velocity vector would be directed horizontally, and we want to work out some kind of relationship to find out what the maximum safe velocity is. How fast can the car be moving and stay in contact with the road? All right, that's the question. And so we're really in identifying what kind of a problem this is. It's clearly a Newton's second law problem, but it's for circular motion because of the way the problem was stated. And what that means is we will be able to use our equation for the centripetal or the radial acceleration as v squared over r. And we'll get to that point in just a minute, but it's important to realize at the outset that that's going to be one of the tools that we will use. And what we're looking for then, we're trying to find the v max that will keep the object, the car in this case, in contact with the road. We don't want it to go flying off. Now what about developing a solution? Well, first we're going to draw a free body diagram, and I will draw it over here because it's closer to where the sketch actually is. Here's the car at the very top of the circle, and so you have to ask yourself what forces are acting on it when it's at the very top. And if the car has a mass m, right, then the weight mg is directed downward. That's the earth pulling down on it. And at the very top, of course, the road is pushing up on the car, and that's the normal force of the road on the car's tires. And when it's at the very top of the hill, then that normal force is directed straight upward. I will choose a coordinate system where the y direction will be directed upward, and so we can go ahead based on that and write down Newton's second law. Now wait, you might be asking, aren't there other forces? What about the direction of the velocity? Well, there's no force acting in that direction, and so the car is not accelerating. The car is moving at a constant speed, so there's no net force in that direction at all. So we can proceed to write down the sum of the forces in the y direction. And of course, at the top of the hill, that y direction is also the direction along a line that goes through the center of the circle. And so we'll be able to use this radial acceleration expression in just a minute. So ma sub y is on the right-hand side of the equation. So, keeping with my sign convention, I see that the left-hand side should be n, the normal force, minus mg, the weight, equals the mass times this y component of acceleration. Well, what we've just learned about circular motion tells us that that acceleration has the form v squared over r. Only now, remember, that's directed towards the center of the circle. So at the very top of the hill, the acceleration vector is downward toward the center, which is in the negative y direction. So I'm going to put in here minus v squared over the radius, which I know is the height of the hill. That minus sign is important, and I could have chosen my coordinate direction differently. I could have chosen the y direction to be positive downward. All that would have done is it would have flipped the terms on the left-hand side. So the left-hand side would have been mg minus n, and then the right-hand side would not have had a minus sign. And I'd still get the same equation. So you can do it either way. I've just chosen to do it in this very straightforward manner. So now we see that there's a relationship between the normal force and between the velocity. And let me just solve for the normal force. Solve for n here. I'm going to add mg to both sides. So n equals mg minus mv squared over h. And something interesting about this, it shows that as the car's velocity at the top increases, the normal force decreases. And that's very important. That observation helps us understand what the problem's really asking, because the physics now shows us that the faster you go at the top, the less normal force there will be. And at some point, if the speed is too high, the normal force will go to zero, which will mean the tires will fly off the hill and the car will be airborne, and that's not safe. Okay, so by inspection we see, and here we're getting into the evaluation step here, so when v equals v max, when we just have the maximum safe speed, then n will equal 0. N equals 0 means your tires are just barely still on the road surface, but they're on the verge of flying off. So that tells us the maximum safe speed. So all we have to do in this equation is plug in n equals 0 and solve for v, and that will be the maximum speed. All right, so I'll go ahead and do that. Take this equation right here, and we write it as 0 equals mg, right, minus mv squared over h, or mv squared over h equals mg. I can divide both sides by g, or by m, sorry. The masses cancel out. So that means this problem is going to give the same answer no matter what the mass of the vehicle is. So this tells me that v max, I'll call it v max now because that's the condition for the normal force to go to 0. v max is equal to gh, or v max is equal to the square root of gh. And I don't have any numbers given, so that's basically as far as I can go with the answer. Units, I can definitely check the units to see if they work. What I'd have for the right-hand side, right, is I'd have the square root of meters per second squared times meters, because h is in meters, and that is meters squared per second squared. The square root of that is meters per second, and that's what I expect to have for an expression for a velocity. All right, so what we've learned in this problem is how to incorporate this acceleration formula when we have a problem involving circular motion. And we also learned something interesting. Whenever there's a problem that asks for what's the condition for an object to leave the road surface, or for something to fly off of a surface, that comes from the expression that the normal force goes to 0. And that's what we had to use here in order to take the last step towards solving the problem. I hope this is helpful as you tackle the homework problems, and we'll do more of these in class.